continuing this book from last time on the categorification of quantum groups using category.
Okay, great. Thanks for coming. So the plan of today's talk is first to describe and recall what we did last time and describe some properties of the Fukaya category that we have. So describe the gluing and cutting properties. Properties of Fukaya category. And then I'm going to deviate a little bit. I'm going to start afresh and talk about what is this Kapranov-Schechtman they had a paper about shuffle algebra and perverse sheaf, which is a beautiful paper, where they proposed the notion of a factorizable perverse sheaf and how it's related to some Hopf algebra, the special kind of a Hopf algebra that's called a primitive bialgebra. And they proved that factorizable perverse sheaf C is equivalent to this primitive bialgebra. And we're hoping to give a categorification of this statement. In particular, we're going to give a definition for what is a factorizable perverse Schober. If sheaf is like some functor with value in vector space, Schober is something, some functor from some domain category to the category of categories. And this primitive algebra is a special case of Hopf algebra. And for example, UQ G minus is a special case of this primitive bialgebra. And yeah, the third is categorification. Of factorizable structure. So in the third part, I will just talk about some general phenomenon from symplectic geometry to perverse Schober or factorizable perverse Schober. Okay, so let's first say what we had last time. So recall. The setup is let's be a little bit general. So G is like an ADE the algebra, and say it has as L5 the Dinkin diagram, and let I be the set of simple roots, or the nodes of the Dinkin diagram. So I'm going to define lambda plus to be the you can say the positive cone generated by the set of nodes, or let's say more concretely, I from 1 to R, the rank of G, some Ki and alpha I. So alpha I is the simple roots labeled by, well, let's just identify this with 1 through R. And the Ki is non-negative integers. Okay. So lambda plus. And we have a space for given for any alpha inside lambda plus. We have a space called the y alpha, well, which is the same as I'm just going to use some this changing name for notation. This is the open Zastava space from P1. Of P1 mapping to G mod B, and sending infinity in P1 goes to B mod B. So this is the mapping space of such space. Holomorphic maps, and degree equals to alpha. Here's the degree of G mod B. Degree is an element in H lower 2 G mod B, which is well, here I may mix up a root or co-root. It should be like it's like a co-root that is in G, and if you're willing to identify this lattice with a co-root lattice, then this is that co-root lattice. But here we're doing ADE bialgebra, so it doesn't matter that much. All right, so this is our Y alpha. That is a space, and this space has a remarkable map. It's called a pi alpha. Pi alpha, the image of pi alpha is denoted by C alpha. So C alpha is a set of I-colored divisors in C. So what is I-color divisor? This basically is just a linear combination of points in C, but it has a coloring. Some from, say, J from 1 to N, so Zj and Kj, where Zj is a point in C, and Kj is an element in the let's call that multiplicity space. Multiplicity space. Okay. Okay. So this are, or you can say this is 0 cycles in C with a coefficient in lambda plus. Okay. So what is this map? This map basically is taking a holomorphic map from P1 to G mod B and extract its intersection with the Schubert divisor in G mod B. So there are some Schubert divisor di in here, which is given by say choose a B minus Si mod B. I hope I'm not mistaken. And this intersection of the image of P with this divisor, and including the multiplicity, will give you this colored divisor in C. And it's C, not P1, because we know the infinity of a P1 maps into something very smooth. It's it maps to just this point. It's a smooth point. So let me just do one example. So last time I only talked about the SL2 case, but I just want to begin today's talk with this general setup to show that all the things we say can be generalized. So let's still go back to SL2. Here P1 is G mod B. And here we can have this opposite superstratification, which is this C union infinity. Infinity is like a B minus. And this is B minus just. And if you have a domain P1 that maps to the target P1, that since this infinity to 0, here 0 is a very smooth point in this strata, then it can be represented, say, Qy mod Py, say degree P is K, and degree Q is less than K. So P is K's power. And K0. And the divisor I was talking about is intersection with the infinity of the image. So that corresponds to the divisor of at infinity of Q mod P is the roots of P. So if you factorize this into YK, this is just going to be the sum. Sorry, this is this summation doesn't mean summing them as numbers. Just to bracket, it means like 0 cycles. A formal sum of points. So this pi map, this pi alpha map, it just goes to send this C alpha O to C alpha, because here we only do SL2, just thinking node is one node, so the multiplicity space is just non-negative integers. So here, say alpha is just K times alpha 1, and C, no K, just sim K, C. And the map is sending Q mod P to roots of P with multiplicities. All right. And last time we said that our space setup not just have a space, but also has a superpotential on it. This is a W alpha goes from Z alpha to C. So in general, it's a bit hard to write down explicitly, but in SL2 it can be written down quite easily. So W alpha sends to Q mod P. The Q mod P is of the form UI y minus yi, I from 1 to k. Then this is just the sum of UI. Okay. All right. So now I want to point out that the thing that makes everything works is the factorization property. Factorization property says that if we have a space that fiber over certain like symmetric product or colored symmetric product, then you expect the fiber over this space to have some nice property. Yeah. No, this is only for positive alpha. Alpha, this guy. Yeah, this degree has to be non-negative because this is like the image of a holomorphic curve. It has to be non-negative. Okay. Well, I didn't quite say what is the C alpha is a color divisor of C with total weight being alpha. So this collection of alpha j sub alpha kj has to equal to the total alpha. So the factorization property of this open Zastava, or more generally Zastava, you can maybe some historical reference is by Finkelberg, Mirkovich. They have a paper called the semi-infinite flag. Like part 1, where they discuss this kind of a factorization property, section 6. If you're interested in this. Okay. So this open Zastava has a long history, I guess. I'm not an expert at all in this subject. So there's introduced by Boris Fagin, Edward Franco, and then before that maybe Williamson, Lustig. Well, this have a deep representation theoretic roots. So this factorization property is not a new property that we discovered. Yes. The pi sub alpha is sending a map phi from P1 to G mod B to the you can say the pullback of the divisor, the Schubert divisor. Schubert divisor is D1 union DR. We don't use infinity to pull back. We just say you have some divisor in G mod B. You pull back to get a divisor in the domain P1. Yeah, and yeah, infinity. Yeah, the domain infinity doesn't meet the divisor, so the divisor lands in C. Okay, so the factorization property. So suppose you have a two disjoint open subset, U1, U2, in set C, and you have, say, two vectors, say, alpha and beta in lambda plus. Then you can consider the two operations. One operation is that you consider U1 and let me introduce some notation here. So U1 subscript alpha is basically a straightforward generalization of this guy. I just put that many points, like I color divisor with total weight alpha inside U1. And U1 alpha times say U2 beta naturally sits inside. So because U1, U2 are disjoint, U1 disjoint, U2 is alpha plus beta. Okay, so this is an open embedding. So we can consider the pullback. So factorization property is just saying, U1 alpha, U2 beta. Let's put this total C. And here you have a pi alpha plus beta. And over here, you have you can do the sorry, let me just it's pi alpha inverse, oops, of U1 alpha times pi beta inverse U2 beta. And we have a inclusion here. So basically, if let me just draw a picture. Suppose you have U1 and U2, and some points here colored, let's say 1, 1, 2. It's colored like 2, 2, 3, for example. So you have U1, U2, and some points freely moving here and moving here, and you can either view them as defining a point configuration in the total space with its total weights, and you look at the fibers over them, or you can just look at them individually and take the fiber over them separately and take the product. So the Zastava space has the property that this forms a fiber product square. Concretely, let's say what's going on here for SL2. For SL2, suppose you have like say 2 points, the 2 points in U and 3 points in V, and UV are some disjoint open subsets in here. One can consider points in this Zastava space which are given by these fractions of the form P1, Q1 over P1, Q2 over P2, where roots of P1 is contained in U, and roots of P2 is contained in V. And P1 is degree P1 is 2, degree of P2 is 3. Okay. So this factorization is simply presented as addition here in the SL2 case. Okay. So this space itself has factorization property. Our superpotential luckily also has a factorization property. Recall that our superpotential is given by extracting the residue over each pole, and we take the total sum of residue. So the total residue of this polynomial is the sum of residue of this polynomial plus this polynomial. So that's also the our space and the superpotential both satisfy the factorization property. All right. So I say. So the alpha O and W alpha, those are factorizable. Okay. So here we also have a special property because we're working over the base is a C. C has this translational action. You can move the point left and right, and like if you think of a polynomial Q mod P is of this form, you can keep UI fixed and changing this yi around. So that defines you certain lift of this translation action on C to the total space. And our W alpha is also invariant under that translation action. Okay. So that's like basically recall the property that we, the geometric property that we have for the space. So now let me specialize to SL2. Okay. So we have, let's call that YK over some KC. All right. So, so our theory provides the following machinery that can assign certain inputs to a category. So what's the input we can assign? So we're going to define the domain category. Domain category is going to be with the object. We call that multi disks with the stops. Here, multi means like you can have several such disks, and I will draw this disk with stops like this. And also with multiplicity. I can put a number 2 or 3 or something like that. Where this picture is supposed to represent a locally closed subset of C, where it's like the open square union with the two boundary edge. Similarly here, and these we call the stops. And this multiplicity, these numbers are just an element in the positive co-root lattice. So these are the objects, and morphism are going to be closed embedding. Closed embeddings. So for example, if I have some disk like this, I can embed into, say I'm going to draw a bigger disk in a different color. Okay, so the bigger red disk has like 4 stops, and the white disk has 2 stops. It's a closed subset of the ambience of the target space. Of course, it's not closed inside big C, but it's closed inside the target. And this is the example. A non-example would be like this, for example. If it's sitting inside this guy. Okay, this would not be allowed because the image of this white guy doesn't contain this edge, this part of the edge, and so it's not closed inside the red guy. Okay, so it's closed embedding, and under closed embeddings, this actually forms a pole set. I don't need to tell you what the compositions are. So this is, you can, if you're familiar with Fukaya category of Liouville sectors, these are called disk sectors. But we put in some multiplicity there. And also, closed embedding, you want to add up your multiplicity so that it matches with the target multiplicity. Okay. And what our theory allows us to do is to assign a category to these pictures. So the functor we have is called a Fuxim, say SL2, say assigns to this N. This is the thing we studied the last time. This corresponds to a disk with 2 stops. So it's category of the cube N horizontal C star C to C, where W is a W fiber plus the sum of Y squared. This space was what we call this Z, call this Y. This is the Yn space. And this part of the superpotential is what it's like the fiber-wide superpotential. That's what we call this Wn. And this is coming from the choice of the base having 2 stops. So it's the Yi squared. If you have more stops, I just do Yi to that number of stops. Okay. Here I'm like swept a lot of choices under the rug. For example, the choice of symplectic form, and this choice of dilating this picture into this picture defined over the big C instead of just a finite disk. Exactly. It's like the machinery we use to define this thing is like involves a lot of choices, but the end result only is like depends on topological data of the input. Okay. So this tells you what to assign to one of such disk with stops. But if you have several such disks with stops, what to consider, then it sends disjoint union to a tensor product. So Fuxim SL2, say D1 disjoint union D2. So Di is an object like multi-disk with stops to Fuxim D1 tensor product D2. Okay. Yes.
So they defined what this is for this stops.
This is for this with doesn't matter for this with any stops. Right. You're right. Yeah. So I should be more general. Tell you what's the thing. Say for M stops, then you change this to N. Well, yeah, this, how to say, this guy has a definition that depends on the actual geometry. And here, this is just a shorthand to tell you what the category up to equivalence is. Yeah, so it's not right to say that's equal to, you have a definition, then it's equivalent to that category. This is like you have this infinitely large disk, and you put the stop symmetrically on the boundary. That's right. Right. So the honest, let's say, we're looking at honestly like Lagrangians living over this space, where you do consider like Lagrangians, say for example, whose shadow are like that, but can be more general than that. And then you have to complete the space. This is technically speaking a Liouville sector domain. You have to define what does it mean as a Liouville's sector domain in the total space, and then show that that space can be deformed into this more regular space. Right. You're right to question that this is not a definition for what the category is, but it's equivalent to the simplified description over there. Maybe a more elementary one, we usually call it Fuchs-Sim GL11, or just omit this GL11 altogether. It's literally just the category of the symmetric product. Say, if I have something like this, I'm just directly just defining symmetric product of this disk and take the category of it. There's some caution to be said about how do you make sense of this guy as a Liouville sector, what happens if multiple points collide to the boundary, but those can be taken care of. All right. So yeah, that's our current paper in progress is about making such a symplectic construction more precise. Okay, anyway, after you define this category more carefully, you would have such factorization property, where given this disk with a stop with multiplicity, you can consider its Fukaya category, and that should be corresponding to each individual parts of Fukaya category tensored together. Okay. Okay, so such assignment send object to this kind of category. And how about the morphism? Morphism, it sends to, let's call that the GPS inclusion. GPS stands for Kapranov-Schechtman. So suppose I have D1 inside D2 closed embedding. I'm going to send the category associated to D1, the category associated to D2. This may not be closed embedding, just a map. So this is assigning maps to closed embeddings. So for example, is my D1 is this kind of a thing. two disks, each with two stops, and I put like a multiplicity 2 here, multiplicity 3 here. So a typical object in this picture would be like a Lagrangian in the, or just lines in the disk, and you specify what is a fiber Lagrangian over each point. So without any decoration, I'm assuming I'm going to use a T fiber over each line. Where recall last time we said the T fiber is a Lagrangian of the form like this. Okay, so this is a typical object in this category. And let's say, suppose what is D2? D2, let's say, is this guy. The pair of pants, pair of half pants. And the D1, including D2, is so that the inclusion image is these two legs. Okay, so this inclusion D1, D2 induces a functor from, say, Fuchs sim of this guy to Fuchs sim 5 of this guy. Okay. Last time we talked about the action of the raising lowering operator. Here we can give a more systematic way of realizing the lowering operator. So that brings us to the key player in this picture, which is a disk with two stops, or a strip. We call that strips. The good thing about disk with two stop is that if you concatenate, how to say? If you have a disk with two stop with N1 here and another disk with two stop with N2 here, it embeds into disk with two stop of N1 plus N2. So this behaves like a graded algebra, and it indeed will be part of the structure for this primitive bialgebra, which is a graded algebra in particular. So if we assign AK to be the Fuchs sim of K here, then we have operations of AK tensor AL goes to A K plus L. Okay. Because AK tensor AL, this is Fuchs sim of K tensor Fuchs sim of L. And by factorization property, is a Fuchs sim of KL. And this includes into a strip, maybe longer strip, with multiplicity K plus L. Yes. Well, this is, I just call that GPS inclusion. The D1 actually doesn't just represent the geometric space of the disk, it represents the symmetric product of D1, take the pre-image into the Y space. Okay, and that Y space, and the Y space associated to D1 includes in the Y space associated to D2 as sectorial inclusion. And the closed embedding, I do need this total multiplicity to match. The total multiplicity D1 is the sum of all the multiplicity in each disk. Equal to sign. Yeah. Otherwise, the dimension of the space doesn't match. All right. So at this moment, you should be pretty happy because you have a category, a family of categories AK, and they have some monoidal action. So if you don't want to carry all these subscript around, you can just define A as a sum of all the Ks. And we also have A sub 0, which is just going to be Fukaya category of a point to be just a vector space. The unit in a tensor in a monoidal category. Okay. So these GPS inclusion functors also has an adjoint as part of the benefit of having enough stops. So these functors has adjoints. Has both right and left adjoint. But particularly, I'm going to use the right adjoints for further constructions. And I'm going to tell you how to think about these adjoints geometrically. Usually, adjoints are defined by some universal property, and it's very hard to understand besides to use this definition. But here, we can realize this adjoint in a geometrical way. So, realization of realization of adjoint. So for simplicity, I'm just going to consider a disk with one component. So let me first define a operation called flip disk. Here I don't actually flip the disk. I just change the boundary type from a stopped boundary to a non-stopped boundary. Just flip solid line into dashed line. So if D is this, forget about the multiplicity, then D flip is going to be like this. Okay, so you can talk about the Fukaya category. Say focusing 2. And you may wonder, okay, these two disks they're both disks with 2 stops, so they should be the same. But how are they going to be the same? There are 2 ways. There are many ways. In particular, one way is to rotate. You can see rotate the boundary. Rotate boundary. Rotate boundary clockwise. Clockwise this way. So I call this R minus because clockwise is a negative direction. So this AB goes to this AB. The other way is to rotate the whole thing counterclockwise. So by R plus, AB goes to AB. So for disk with n stop, its flipped disk is also disk with n stops, but in the complement spots, and you either rotate left 1 click or right 1 click. It's R plus, R minus. So this geometrical rotation can be realized as simplex homomorphism. So on the category, on the Fukaya category, you also have corresponding functors with the same notation. Okay, so that's one part of the story. You flip the disk and rotate. Another part of the story is what I call a cut. So this cut is in some sense dual to the GPS inclusion under closed embedding. This cut, if you wish, is the viterbo restriction along open embedding. Okay, what do I mean by that? So suppose I have a disk like this. I can tell you an open subdisk in here, sitting, say, in this middle part. So this D1 inside this D2 is open inclusion. Okay, this is the open subpart. And there's a there's an operation called cut, or in general restriction, that tells you, okay, restriction for this Fuchsim of D2 can restrict to Fuchsim of D1. It can be more general, such restriction. For example, say D2 is this kind of disk with 3 stops, and I can consider open subset the union of these 2 pieces. They're open subsets. So call that union D1. Right. So this functor, by the way, I didn't introduce this shorthand. This is the Fuchsim of this. This is this D2 with all possible multiplicity, the sum over multiplicity of this D2. Let maybe say the underline here to mean there's a geometric disk underneath it. Okay. So one can have such restriction functors.
Why is
Open.
why don't intersection
So you're asking how to define such restriction functor.
Yeah, I mean, even the conclusion itself, like, if I perturb a little, things will escape.
Yeah, let's do one. Yeah, let's do one example. That's a very good point for how this viterbo restriction works.
Is that stuff older than GPS?
GPS talks about the viterbo restriction as a stop removal in some subset of viterbo restriction. But that idea exists more generally. I'm not sure whether viterbo is the first to consider such notion, but most common examples are there. So what's restriction? So to consider the example, let's say for have a pair of pens, and we just do the usual category of it. And one can consider some open subset. Here, just the cylinder. Okay, and one can consider the restriction functor from this pair of pens to the cylinder. Category of the cylinder. Okay, so what does this do on object and what does it do on morphism? Suppose you have a Lagrangian, it's like it's a different color. Suppose you have a Lagrangian like this. You can restrict to get a Lagrangian, just take the geometric restriction. Suppose you have a Lagrangian that, I don't know, looks like looks like this. Then naively you would say the Lagrangian you end up will be L1 plus L2 if you just take the geometric Lagrangian coming from that. But actually this Lagrangian can be deformed into the Lagrangian that's totally contained in here. So what you should get is a Lagrangian. If you define your restriction functor in a well-defined way, what you obtain your isomorphic object should restrict to isomorphic object under here. So whatever you have, your naive restriction must be corrected to be equivalent to this guy. So in this case, we understand what the correction is. The correction we understand is given by this holomorphic disk bounding your original Lagrangian and with a puncture ending on the boundary ripcord. And that ripcord tells you I should connect this to Lagrangian by a connecting morphism. So the restriction, you can say in one short, is like is well defined modulo technical details by just restricting the geometric Lagrangian, and together we will add in some corrections coming from disks that you cut off. All right. So this kind of a cut is a special type of viterbo restriction. For example, we want to consider, let's say, a disk with multiplicity, say, 3, and I introduce a cut in the middle. I want to say this guy 2 and 1 includes into this disk. So the restriction functor being contravariant will say, okay, the Fuchs-Sim of this guy to restrict to Fukaya category of this guy tensor. Let me just draw the tensor like this with Fukaya category of this guy. And you can say on the object level what happens here.
You want to pick up 2 and 1 somehow overlapping a little, or no?
No, they're open immersion. So D1, D2 are separated by a little gap. Well, this is an open boundary, so it doesn't hurt to say the actual overlap touch on the boundary. Okay, so on object level, what's going on? Suppose I have a Lagrangian in here. It's like these 3 strict lines. So to restrict it to here and here, let me draw pictures. You can just decide which points stay on the top portion, which points stay on the bottom portion. So you can imagine there are 3 points running on the strand, and you have to consider different partitions, which is on the top, which is on the bottom. So on the most naive level, we would have like this picture, or this picture, or this picture. Okay. So on the object level, you input this object, you apply restriction functor. Naively, you would get a direct sum of these three objects. Of course, we need to worry about whether there are disk corrections or not. In the case where there's the T-brane as a fiber, you can compute there's no disk correction available because those disk corrections give you degree 1 endomorphism between the objects. And here, all the T-branes have no degree 1 morphism between objects.
I have a question about this. So, we could contemplate like two orbital branches.
Yes.
One where these two strands at the bottom just go all the way up.
Mm-hmm.
In one guy, actually three. In the other guy, or you can contemplate somebody who goes with single lecture.
Like this?
Yeah.
Mm-hmm.
No, I wanted to have the same restriction at the bottom. My question is whether it would have the same restriction to the bottom part, but so for example, the red guy could have gone around one of these holes. How would you tell that?
You mean suppose you have the red guy that goes like they go up and go around and come down.
Exactly.
Right.
Or a red guy that goes,
to the other hole.
To infinity. How
Yeah.
This isn't supposed to be like
this. Yeah. So under restriction may lose information.
You will.
Yeah. Okay. Right. You can go up here. You can go up here. They may end up restrict the same object.
So in particular, this guy you will not be able to tell from the guys from a direct sum guy, right?
That's right. Yeah. That's right. That's right. Because there's no disk helping you to tell them apart. Okay. So we have these restriction functors, and in this example, the restriction functor here is just this three direct sum of these three objects. And you may think, that's very good because for this kind of object, restriction doesn't do much stuff, but you need to worry about the morphisms. Like this guy has very interesting endomorphisms, this new hack 3, and you would end up having an embedding of a new hack 3 into the endomorphism algebra of this guy. Okay. I use the word embedding because I know that this map doesn't lose information on morphism space. Oh, sorry. I should take back the word embedding. Yeah, if I sum over all the multiplicity, I know it will not lose information, but I cannot guarantee it doesn't lose information in our choices. I'm not sure. So anyway, there's a functor. So this kind of a cut functor is this special type of restriction functor where I introduce a cut in the middle, and I restrict to certain multiplicity splitting to the two parts. So the adjoint of merge will be now realized as a composition, as a conjugation of cut by this, let's call that duality functor. I call this a duality functor. Because in some sense, this Fukaya category is due to this Fukaya category because the stop just mismatched. So if D1 with a certain multiplicity is D2 is a closed embedding, let me denote that by little I. Then I have I lower star. This was my just notation for the corresponding functor from the category. And if I consider the flipped case, D1 into D2, this I flipped is open embedding now. just to do an example, just to make sure, suppose this guy is D1, this bigger guy is D2. This was closed embedding. Now I flip the open and close the boundary. This is D2 flipped. And this guy is D1 flipped. So indeed, now D1 flipped is mapped into D2 flipped as open embedding. For this open embedding, I can have the restriction map. I'm sorry, maybe it doesn't matter for notation, but I like to think about this as left adjoint lower shriek. And for this, I have this restriction map. That's the Fukaya of this D1 shriek, sorry, D2 shriek into okay. So this is a restriction. Okay. Now the statement is that the right adjoint of this inclusion I lower shriek right adjoint is defined to be first to the negative rotation composed by the pullback into the right rotation. And if you care about the left adjoint, you just change the way you conjugate stuff. So these are the adjoint for the inclusion guys. Okay, I'll just do one example and then I will go on. For example, my D is this guy. This is my D2, and I'm going to have my D1 to be the side here. This is my D1, viewed as a subset, closed subset here. So D1 is closed. And let's consider first what is the, say, I lower shriek. What is the push forward along inclusion, close embedding that we discussed before is this guy. So it goes inside as this object. All right, now I want to say for different testing object, I want to do the I upper shriek. Let's call it right adjoint as I upper shriek. What do I do? To say where does it go on upper shriek, I first need to rotate counterclockwise my disk. So to apply R minus, I end up with the disk where the boundary are, the color are swapped, and I push along my Lagrangian so that it goes along the right. Okay, so this guy will go to to here. We draw the main part the same and just twist the boundary part. And this guy will be okay. Right? I'm just twisting the boundary part. And then I do the cut. Now, this is a D2. This is a D2 flip.
So your allowed operation is really just a change of the boundary color, and you can think of this change of the boundary color as coming from the left rotation or the right rotation.
Exactly.
It's not necessarily applied toward any discrete angular rotation.
No, yeah, that's right. That's right. Now I do the cut. Now the cut is going to be cut along this open boundary. So I'm going to do the cut that split 1 and 1 in terms of multiplicity in the top guy and the bottom guy. So in this case, nothing interesting happens. It shouldn't. Okay, so I need to keep one multiplicity here, so that's give me, this strand will belong to this top part. And this guy is already belong to the top part, so the bottom guy is only use this Lagrangian. All right, and then finally, I rotate back. R plus rotating back. This will give me so gotta be really careful. I need to have this zigzag, but they're basically straight lines. All right. And it's a theorem to prove that this sequence of operation indeed reproduces for you the red adjoint. Okay, so suppose now we have this nice category Fuksim functor that takes this kind of a domain category into the category of categories that sends close embedding to this GPS inclusion, and having all this all the adjoints exist. What does it buy me? What it buy me is that we can now think of category Fuksim of two disks that overlaps in terms of category of each individual part. Let me try to say that again. We have this strip is sent to a monoidal category, and any disk with stops, each stop is sent to a module over that monoidal category. So we can talk about monoidal tensor product, categorical monoidal tensor product, and that corresponds to gluing of surfaces. So theorem is that let's call it bar gluing works. Okay. And the word bar means like bar resolution of derived tensor product. So if D is a union of D1 and D2, union, then we can overlap over a hypersurface. Let me just draw it. And here's let me maybe put it in a better way. So this part is, say, D1, and this part is D2, and this guy, H, is D1 intersect D2. This is a strip. So you can say it's like a colored neighborhood of an interval. And that interval does not end on stop. It ends on an open boundary. Then the Fuchs theme with all multiplicity D is FD1 tensor as a monoidal module over this monoidal category of D2. Yeah, it's equivalent to that. So concretely, this is realized as a bar resolution for each multiplicity D here, K here. You can write a finite colimit diagram of depths at most K that give you this bar resolution. So for simplicity, I'm just going to do it for the multiplicity equals to 1 and 2, just to show how it connects to the classical case. So example. So it's a Fuchs theme of suppose I cut it over here, and I consider the total multiplicity is 1. And this can be written as just a Fuchs theme 1, 0. And Fuchs theme 0, 1. Let's put one strand on the left or one strand on the right. Or Fuchs theme in the middle one. So just as we'll do a bar resolution for a tensor product, over this base field, I have two maps where A can merge into M or A can merge into N. Here, these strands can be belonging to the left or included into the right. And this equals to the colimit of this diagram. More precisely, every piece maps to here, the colimit maps to this guy. Yeah.
When you say that you have two disks glued along the hypersurface always has to be straight.
Yeah, that's right. There's not much hypersurface on the curve. Right, it's not a circle, so to speak, yeah. Okay. And this is, you can realize this is the classical like GPS gluing, where the Fukaya category of the middle strip maps to the Fukaya category of the left part and maps to the Fukaya category of the right part. So the usual GPS gluing is K equal to 1 case. Now K equal to 2 is where the interesting thing happens. 2. Now on the first level, I'm just going to write schematically 2 can be obtained as 2, 0, 1, 1, or 0, 2. I split the number 2 into 2 halves. So the corresponding category have this kind of a functor. And now if you further split them, you can get 1, 1, 0, 0, 1, 0, and 0, 0, 1, 1. Sorry. Here I'm using a version of the reduced bar resolution where the intermediate buffer zone has to contain non-zero multiplicity. Otherwise, that's reduced. So this guy will map to here, 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 and here. And finally, you get 0, 1, 1, 0. Okay. Now, if you observe or taught like calculus or high school algebra, you notice that the multiplicity 1, 3, 3, 1 seems to remind you of something. Reminds you of, it reminds me, at least, of a cube. Where this level, and this level, and this level, and this level. The level of, it's a cube, and the level of vertices on the cube. And this reminds one also of something that's like a check covering of a space. If you think there are 3 open sets, the 3 open sets, and we'll call this U1, U2, and U3. If you identify this top level as U1, U2, U3, and this is U1 intersect U2, U1 intersect U3, U2, and so on, this Venn diagram of this check covering also will give you this kind of a picture. And that's the key of the proof why this guy works, because we can realize the right-hand side, the colimit diagram, as a check covering of the total space. And then we check that this kind of open set forms GPI's Liouville sector, and the GPI's Liouville sectorial cover then can be applied to give one the kind of multiplicative check cover. Okay, so that's like the basic idea for the proof of the bar-gluing works. Now, the fact that bar-gluing works doesn't rely on the actual setup of the detail of the setup for our problem. It works more generally. In fact, whenever you have a factorizable fibration, so fibration, something like this, where alpha can range in some like semi-group or free semi-group, and where this guy is an I-colored divisor, product of symmetric space, and whenever you have this factorizable superpotential W alpha, then you could get such family of categories. And you want to say, okay, what do we get? So we can mimic this Fuchsim construction. What is a Fuchsim construction? It takes input this multi-disk with stops and output a category that satisfies some nice factorization property. Tensor product give you The disjoint union give you tensor product, and the bar gluing works. It sends disks. This stops to category and sends close embedding to functors with adjoints. And also bar gluing works. Because all this argument about bar gluing, we don't require much about the knowledge of the fiber. All we need is just some nice covering of the base symmetric products. And there's some other properties, like if I give you a disk with just a one stop, then can only put 0 number of strands in it. And if you put any one strand in it, it's going to be 0, things like that. And also, the Fuchs of this disk with 3 stop admits a SOD, which I will talk about later, but SOD decomposition. Which basically just says that because of the you can pick a collection of say subcategories, and there's some directionality about who can map to who. And if you remember the direction of wrapping, if I give you 2 Lagrangians, L1, L2, then by the wrapping direction, L1 can map to L2, but L2, when it wraps, can never intersect with L1, so there's no wrapping. So no map from L2 to L1. So this kind of argument can give you isolated decomposition. For example, if I give you like 2 strands, you can consider 2 strands being of the form either 2, 0, or 1, 1, or 0, 2. And because of the wrapping condition, 2, 0 can map to 1, 1, 1, 1 can map to 0, 2, but you cannot map backward. So this kind of SOD comes for free to you from geometry. Our basic proposition for definition for perverse Schober is just these axioms. Okay, but let's stop for a little bit and plus SOD, yeah, including SOD. That's the most important part.
Do you have any other examples of a factorizable vibration from you?
There is a let's call it a Seidel-Smith space, where it's a close cousin of the open Zastava, but without the superpotential. So that also forms a factorizable space.
So this isn't like specialization where you just don't have any stops.
That's right. You don't have a fabric stops. Right. So this story I'm describing is like a pure gauge theory Coulomb branch. You can also add in the defect.
I understand mathematicians who came up with these last spaces. They were trying to come up with some geometry that behaved like CFT. And these are the things that behave like CFT. Categorifying.
That's right. Okay, so let's forget about these categories, but remember the pictures. That disk with boundary stop and Lagrangian strands in it, and let's try to relate our setup to this shuffle algebra. So relation to shuffle algebra and perverse sheaves. So this is a Kapranov-Schechtman refers to that paper. So we can first think about what is a shuffle algebra. So given, let's say, given amount, maybe also there's an older paper by Rosso. So what is shuffle algebra? There are three kinds of a shuffle. There is this small shuffle, big shuffle, and the middle shuffle. So what's the setup? Suppose you have H, let's say a Hopf algebra. You can, for simplicity, you can take it to be just base field. And suppose you are given M, which is a Hopf bimodule. There's a Hopf bimodule means it's so you have action from the right, you have action from the left, you have a co-action. Sorry, maybe for people who don't know about Hopf algebra basically is like a bialgebra with certain property. You have a product. Bialgebra means you have a product and a co-product. And you have an antipode as mapped to H. I think it's like anti-homomorphism. It changes the order, like SAB equals to SB times SA. And there's also like the unit and co-unit map, satisfying a bunch of conditions. So the way I like to think about this is to picture your H as a disk with two stops. If there's nothing you remember after this talk, maybe this pictorial understanding of a Hopf algebra is going to be useful, because that's how actually I remember all the axioms, using this with two stops. Okay. So this is a multiplication. This is a co-multiplication. And there's also this antipode. Goes to A and B. It's like upside down, rotating by 180 degree. If I put a Lagrangian in here, labeled alpha beta, they will be rotated to the upside down Lagrangian, like alpha and beta this way. So you can see why the multiplications outer are swapped. A times B becomes B times A. Okay, so that is a Hopf algebra and a Hopf bimodule. The way you want to think about them is this with two stop and with some defect, whatever that means. In our actual example, you can think the defect maybe is a, say a puncture labeled by some highest weight, or it can be a defect, maybe it's just simply a hole, like a Fermat representation. Or it can be, say, a bunch of composite things, just a blob, where you cannot freely move from this way to this way. So for now, I'm just saying, okay, you have some defect by M. And this guy can have action from the left, action from the right, because you can merge this strip from the right and from the left. And you also have the coaction, which I didn't write. Usually people say it's a left coaction and right coaction. The more geometrically, one should think about the up coaction and bottom coaction, because we're splitting off something from the top and from the bottom. So coaction. And another coaction and bottom edge. Okay. Now, given this thing, Rousseau and the people worked before them, they defined two operations. One is called the free algebra, the THM. What is the definition? The definition is the following. You start by having a copy of H and a copy of M and a copy of M tensor over H with M. This M tensor over H with M is that, sorry, here's M. You can have M and M sitting side by side because our tensoring is like horizontal tensoring, and so on. Okay. Now this guy has a natural tensor product structure. So it's a free tensor product. So we have a, sorry. We have so let me just say this more carefully. So M tensor with H with M is defined to be the say the colimit of just M tensor with K with M is okay. So we have this kind of a picture And here, because we're doing this non-derived stuff, this co-limit is just a co-kernel. Sorry, I blank a little bit about what is the product and co-product structure for this guy. So the upshot is that we have another Hopf algebra coming from this construction. Okay, I may get this wrong, but the concatenation is a straightforward left and right concatenation. And the co-product is the interesting one. It's different ways of splitting this strip to top and bottom two part. So you have a choice of deciding which each M whether it wants to go on the top or go on to the bottom. So that's what the shuffle comes out about. It has a easy product but a hard co-product, the shuffle co-product. And there's a related construction, which is categorified in a different way I didn't talk about, is that there's something that's called in a very weird way called a cotensor product. Okay, this guy is really, really bad. This is a kernel or the limit of, let's say, M tensor M to M tensor H tensor M. So you can, from M tensor M, you can either split the top guy from the bottom and a copy of H, or bottom guy from the top a copy of H. So drawing pictures. Can have M, M. H is just an empty thing, disk. So there are two ways to go from this picture to this picture by splitting either the top guy, an extra H, or peel off from the bottom guy as a copy of H. And this cotensor is like the limit of this restriction. Of course, if you are in categorical or derived case, you have to go on and on, splitting more copies of H. That's called a co-bar resolution. So there's a similar thing called a TH co, which is just H plus M. Notice that the initial two terms are the same, which are important because later we're going to use that to create a map from this guy to this guy. Here's M tensor M, tensor over H. And you have M, M, M. So on. So you stack the defect in a vertical way. And, all right, so as a vector space, it's easy to see there's a rotation by 90 degrees, that this is equivalent to this. As a vector space, it's easy to see that these two vector spaces are actually the same vector space because each term are isomorphic. But if you want to create a map that respects the bialgebra structure, that's not the map you want. Okay, I didn't tell you what the algebra structure here. So in this case, the co-product is easy to define. Co-product, remember, is just cutting in the middle. And here, for each such picture, it's easy to choose how do you cut. But the product structure is harder to define because it basically involves merging two columns of M and M into a single column. And that involves all possible ways to shuffle the stack together. So the product is harder to define. So the shuffle product and easy coproduct. And this honest shuffle algebra is the image of a usually denoted by alpha map from this Hopf algebra to this Hopf algebra. You can say it is identity on the degree 0 and degree 1 part, but on the degree 2 part, you don't take everybody in here. You only take those objects that comes from the product of two degree 1 guy. So it's a priori smaller than what you get here. Because when you product two guys together and you merge them, you only end up with a symmetric result. You never get alpha, beta. It's always alpha, beta plus beta alpha. Or this maybe is called a symmetric tensor product. So the relation with our setup is that you take H to be this Hopf algebra to be some like a graded vector space, and M, this module to be the vector space generated by positive roots, or sorry, just simple roots. You will obtain this universal enveloping algebra as a positive half. This is UQG plus. This half may include a carton part as well, and you can see what object dies under this map.
Yes.
I can't reproduce it right now. Yeah.
But Saturn relations already hold for our for the thing that you're assigned to the strip. We assigned to the strip.
Well, yeah, right. So here we're when I say what to assign to this H is not this UQG algebra. This H was something like just the group algebra of the weight space. It's just a.
So in other words, our construction categorifies S sub H, not the pieces.
Right. So you take H to be like this and M to be M to be the finite dimensional vector space generated by all the roots. And there's some like a billion. I forgot how it works. Then you would get. Yeah, this is not the naive commutative group ring. There's some like non-abelian, and you get this UQ UG plus.
I wish you had explained what is coproduct in our setting.
That's right. Let me maybe take 5 more.
I think we have 10 minutes.
Okay.
Yeah.
All right. So in the old story, you can see. What's that? Yeah. Okay. In the old story, you see we only use the disk with 2 stops, but our theory has disk with 3 stops. How's that related to this? And you remember the reason people want to have a Hopf algebra, want to have a coproduct, is so that we can have a tensor product of modules over the Hopf algebra. We can split a group element, algebra element into 2 copies, and then join act on the 1 copy. So this is realized in a different way in our setting when you categorify. We get a trimodule, which is the it's like a triangle, so the notation is still good. So we get a trimodule which has a left A action on the right and a two commuting A action on the right. And we can first see why this decategorifies correctly. Like, in the sense, how can we use this to produce the usual splitting coproduct? So the translation is the following. So suppose we start with an element in A in this algebra. You first act on this guy using, let's label them 1, 2, 3. Your action from the stop 1 to the vacuum object in this category, which means like a 0 strand in here. So that gives you a embedding into this picture. And then you consider the it's not adjoint, or it's not adjoint of 2 and 3. It's basically adjoint of 1 and 2. But anyway, so this pi 2, 3, which is right adjoint of action on 1 and 2. So pi 2, 3 is the restriction map to this two side. Okay. So in other words, you're cutting this apart from the middle to get to this sorry. So one can check that this on the decategorified world doesn't differ too much by just directly splitting this. But
didn't you want to cut off the right part?
What's the right part?
The two strips on the right, not at the top of the bottom. Maybe that's what you want to do.
No, it's not the right adjoint. It's when we do this restriction, you only have to you can only do open restriction to the open subset, the top strip and the bottom strip. Right. The good thing for this pi 2, 3 is that when you act pi 2, 3 on empty guy. Yeah, it is associated to 2 and 3, but so let me explain. So when when we do cut, remember we can only have cut that ends on stops. So yeah, you're right. If you want to compute this kind of a cut, well. Let me explain the relation between that cut and this cut. Okay, so let's call this iota 2, 3 by having this two copies of this algebra acting on the stop 2 and 3, acting on the empty guy, so I call it iota, and that we require this to be a so that is an action. If I fix the multiplicity, say K2 and K3, and iota 2, 3 from AK2 tensor AK3 goes to this guy, it's good. This is a fully faithful embedding. However, if you consider the totality of summing up to K2 and K3, the sum up to the total K, then if you sum up them, K2 to K3 equal to K, this fails to be a fully faithful embedding. The reason is that when they enter the common playground, different components can talk to each other. But on here, they don't talk to each other. So I have more morphisms here. And this morphism data, you don't see them on the decategorified world. So it's only new phenomenon in the categorified case. Okay. So we have this iota 2,3 is acting on the right. And this iota 2,3 together paired with pi 2,3 is identity on this input. However, if you first pi and then come back, you don't get identity. You lose information here. So let me just give you one example, and then we'll quit. If you consider this Lagrangian L, I'm sorry, just losing my mind. If you consider this Lagrangian L, if you first pi it, pi to 3, you will end up with either this guy together with this guy. Well, I drew them like this, but maybe it's not very accurate. It's restriction to the top and the sum of the top and the bottom. So the moving point can either belong to the top or belong to the bottom. That's what the two picture means. However, if you pi 2,3 and then iota 2,3, then act into here, what do you get? You get this guy direct sum with, I'm just drawing in the same picture, is this guy summing up this guy. It's no longer the same as that guy. What's the difference? The difference is that if you correct this with a connecting homomorphism, this delta, then this would be equivalent to this original guy. So that means that your L is your pi iota L, the iota of L, together with a twisting differential. Now, this is not a new phenomenon, because whenever you have a two-term SOD, C equals to C1, C2, and for an object L, sorry, I'm not sure which one is L1, which one is L2. Probably this L1 is L2. You can split into a two-part L1 in here, L2 in here, and an L object. And L is not equal to L1 direct sum with L2. That's clear. But it's indeed equal to L1 direct sum with L2 together with this twisting differential. You can view L as a two-term complex with this. Of course, everything has to be done in the DG or sufficiently derived world, because you can't just remember the ext class between the two objects. You have to remember the actual morphism. And it's this trinion that encodes all such delta in a very the SOD decomposition of the trinion is with 3-stop encodes all this delta information. That's how it categorifies. All right, thank you for your attention. All right, thank you.
You briefly mentioned something about the perverse sheaf. Could you say that again?
All right. Right. Perverse Schober, let's just say some general words. Perverse Schober, say on C, say maybe with possibly some similarity. So I should mention everything I said here is heavily influenced by Decker-Hopf, Kapranov.
If they were coming, we have a bunch of people over there. I think we are, so it's okay.
All right. Okay, that is better. Kapranov. Schechtman, Seibelman. So they have a series of papers discussing the decategorified story, perverse sheaves, and factorizable perverse sheaves, and also the infinity categorical new framework how to think about perverse Schober sheaves in that world. So suppose you have a C with a bunch of signal support. What's a perverse sheaf? Let's say what's a perverse sheaf? It is to associate this with the stops or a multi-disk with the stops to associate to this kind of a picture to a vector space if you are dealing with perverse sheaf. Or if you're dealing with perverse Schober, which they haven't read a paper yet, is to assign these pictures into categories. They can categorify like a perverse Schober in a more functorial way. And this categorification should respect a bunch of morphisms of these disks where it's not just a close embedding of the disk into another disk. You can move the stops around. You can isotope them so they can include a new puncture or inside the disk and so on. So it's like a more sending this cobordism category of disks, embedded disk into the category of categories. So that's a perverse Schober on C. So what is a factorizable perverse Schober? What's the new idea? Is to allow disk with multiplicity. Previously, the total multiplicity is 1. So even though when I draw these pictures, it's like 1, 0, 0 plus 0, 1, 0. It's kind of this guy, it's a plus. So they send this kind of a disjoint union of disk to the direct sum of the output corresponding categories, not tensor product. Now we have a factorizable perverse Schober. It basically sends this disk with multiplicities into categories. And the only new thing is that it replaces the old sheaf condition. What's the old sheaf condition? Saying if you know things about U and V and U, and on the overlap, you know the section on the whole thing, which basically is this kind of a co-limit of this kind of a diagram. But as we have seen in the monoidal world, it's not this additive co-limit diagrams. This more is this monoidal co-limit. Of course, this is not for arbitrary UV. This is just in the case where U intersect V is like a strip. It's the algebra itself. So so if you impose this kind of sort of like the gluing condition, you get perverse Schober. And also you need to include this ISOD decomposition data for this training. So there's a definition for perverse Schober for just the C, say without any singularity, or you can put singularity in. You can also generalize the C into any curve. It's because you're only using local testing object disks. All right, thanks for the question.
When you have the part flowing in hand, you automatically also have the SOD. Provide that by hand. I mean, it automatically gives you this one part thing.
Yeah, exactly. So there's also ISOD gluing, which we didn't talk about here, which is more like a how to say open and closed recollement. What do I mean by that? Suppose you have a space X, and suppose you have.
Can you repeat the last sentence?
This is just fancy French word recollement, whatever that means. Decomposition. I don't know, knows French. It's just say if you have a category, you can try to decompose into basic building blocks. And suppose you have this X1, X2, where X1 is closed embedding and X2 is open embedding. Then you can decompose, say, for example, a sheaf on X into a sheaf on X1 together with sheaf on X2 together with extension data. So you have a sheaf, say, you can have J this is open. You have two recurring moments, let's say. The thing that's relevant for us maybe is like this. I hope it's correct.
Yeah, that's like an exact triangle.
Thank you. Right, that's right. So that's just the sheaf on X. That means SOD from sheaf on X2 together with sheaf on X1. Okay, so we have this kind of a you can say SOD decomposition from this open to closed case. Again, this is the old story. If you have a multiplicity 1, you can split 1 either on the left part or on the right part, and there is a directionality connecting them. And there should be a multiplicative version for this guy. If you have a, Vivek wanted to say the exponential sheaf with multiplicity on the space. So you have a multiplicity 2 here. Then again, you should have like 2, 0, 1, 1, 0, 2, more and more spaces. So that picture is more like schematically written, expressed in terms of this guy. Suppose you have, say, let's call it X2, X1. Suppose you have some picture, some surface like this, where some defect X1, X2 over the disk here, and you want to split the disk into halves. This is kind of a new kind of split. It ends one part away from the stop, one part is on the stop. And you can say, suppose you have say 2 strands on this guy, 2, 0 can map to 1, 1, can map to 0, 2. So your category C should be an SOD of the form C20, C11, C02. And this is C2. So this is a so-called SOD gluing, SOD decomposition of cutting through like this. I should comment that this kind of a cutting has been used by Andy Mannion and Rouquier to study their decomposition of Higa-Floor theory, where the cut is through the stop into this part of open end. And this is also used in a way by the categorified world by these people, where they want to, I forgot which paper was that, maybe it's the sheaf paper, where they say, okay, if I have some singularity like this, you can have some cut like this that can split your space into a space where with one stop and one puncture, and another space like that. So it's like when they cut, they put the stop on this guy and this other boundary. The complement boundary is no stop.
We also, in other words, once you take, if you have 2 of these A-module categories, if you want to take their tensor product, the one that remembers the A actions, you won't do this.
Exactly.
In other words, this is the gluing of this thing.
Yeah. So
in other words, you want to say that my gluing and your operator is the same gluing, the same tensor product.
Yeah, I haven't checked the details yet, but in terms of the philosophy, yeah, it's like this. So this kind of a gluing, you can also ask, can you glue this thing, this end product with categories on the left side, category on the right side? Yes. So if you know how to do this bar gluing, then gluing left, right along this will produce for you this kind of a final picture. And the benefit of having this kind of a redundant bar gluing is, again, you can show, you can have 3 A actions on this trinion, it endows you a action on the result. If you directly write down this very lean, very succinct SOD decomposition, the monad stuff, it's very hard to realize that the action of the A on the top stop. You could by writing down very long formulas, but it's very hard to do this explicitly. All right, that's